temperature increases, the rate constant K also increases. Okay, so there is actually, we'll go over, when we get to this later today, I hope, a related quiz 5 problem, but let's go back a few slides. Okay, so let's see. We reviewed how to determine the rate law by experiment. So this is the way we discussed in quiz 5. So in step 1, you do several experiments. So you change the concentration of one reactant, keep the other reactant concentration constant, measure the rate, do several experiments. Compare the rate with the change in concentration to determine the order of the reaction with respect to each reactant. Then you can calculate rate constant K. So we did that. So let's just review these questions here. So if a reaction is first ordered reactant A, if the concentration doubles, what happens to the rate? It should double. A reaction is, okay, I think we did this. The reaction is second order in reactant A. If the concentration doubles, what happens to the rate? It should quadruple. Okay. If the concentration triples, what happens to the rate? Okay. Reaction is second order in reactant A. Concentration triples, what happens to the rate? Yeah, multiply by 9. Okay. Now here's the second way to determine the rate law for a reaction. Now, in this method here, you actually only have to do one experiment. So in this case here, you do an experiment, you measure the concentration at different times in an experiment. So how would this concentration versus time graph look? Okay, so let's say we have this reaction with A going to products. And this is the concentration of A, and we're plotting A versus time. What would this graph look like? So it's going to look like this. No? It's going to look like that. And it's going to look like that. So it's not going to look at any of these? What's going to look like? Increasing. Pardon?
Should be increasing, right?
Okay, now note this is A is the reactant. So what happens to the concentration of A as the reaction proceeds?
Decreases.
So it's not going to be increasing. It's not going to be flat. So it should be decreasing. But is this the actual form of the curve? Okay, so what should it look like then?
Inverse exponential.
So it's going to look like. It's going to look like this. No? So what's it going to look like? Okay, so I think you're telling me it should look like this.
Yeah.
Okay. Okay, so in this experiment or in this method, what you would do is you would determine the concentration at various times in this experiment. To determine whether it's first order in A or second order in A, what you would do is, the first step, you would assume the reaction order is either first order or second order. Then you would use these integrated rate equations to graph the data. Now these are described in the textbook in section 14.3. So let's take a quick look at that. That's on page. That's on page. That starts on page 475, because that's in section 14.3. Now let me just do something here. How many of you guys taking calculus? Oh, good. Now I last took calculus in 1970 something. So you're gonna have to remind me how to do some of these integrals. Okay, so in this rate, you have A going to products. So here's our rate. The rate is equal to the change in concentration of A with respect to T, and that's equal to K times the concentration of A. And let's assume it's first order. So our exponent is going to be 1. Okay, so again, we're assuming it's first order. Now instead of using this delta symbol, we'll do it this way. So we'll say dA over dt is equal to K times A. And let's rearrange this equation. Let's do this. We have dA over A is equal to minus K times dt. And then let's do this. Let's take the integral of each side of this equation. And this is where you guys need to give me some help. So what's the integral of dA over A? George? You sure? Note that K is a constant, so what's the integral of dt? T. Okay, so this is the integrated rate law for a first order reaction. So what we would do is, based on your concentration versus time data, if you assume it's first order, now your graph, you'll be plotting the natural log of A versus T. And what should this graph look like? Now, before we go on, the reason doing that is remember from, I don't know, I can't remember which math class. Anyway, when you're doing a linear fit of a line, you have this equation, y equals mx plus b. Okay, where m is the slope and b is the y-intercept. Okay, so that's what we're doing here. So if we have y is equal to m times x, okay, then plus b, this is why we're plotting y. We're plotting a natural log of A on the y-axis. We're plotting t on the x-axis, and k is going to represent the vertical line. So going back to our graph over here, what should this graph look like?
Negative straight line, decreasing.
Okay, so you're saying one that should look like this. And what is the slope of this line?
Negative K.
Yeah, so the slope is equal to minus k. So again, you do one experiment, you determine the concentration at different points in the reaction. You would then plot the natural log of A at those different times versus T. If you get a straight line, that tells you that the reaction is first order in A. If the line is not straight, what does that tell you?
It's not first order.
Yeah, it's not first order. Then you would have to try the integrated rate equations for a second order reaction. That's described in section 14.3. And hopefully one of those will work. Now, the other thing with reaction order is that reaction orders are either going to be 0th order, first order, or second order. It's very rare to have a higher order than second order. Okay, we'll talk about why it's rare later on. Okay, so I think I've showed that down here. So here's our example. We have A going to product using method 2, how to determine the rate law. So we did our calculus here, the graph, the natural log of A. Okay, now let's go to part B. What is the half-life of this reaction? So if we take a look at this graph here, note that this concentration represents the initial concentration of A before the reaction starts. So what does the half-life represent?
After the concentration.
Yeah, so the concentration of the half-life relative to A0 would be half A0. So if this is, we'll call this AT, T1 half. Okay, so that represents 1/2 A0. So this is going to represent the half-life here. Okay, so that's the amount of time required for half of the original amount of reactants to react. So for a first order reaction, we can figure out how K is related to the half-life. Now let's do one more thing here. When we're integrating, let's see, I think we're supposed to do it this way, from A0, these are our limits of integration, to A, and this is from 0 to T. So is that going to change our integrator rate equation when we include those limits of integration? Is that what you call it? Those limits of integration. So how is this equation going to change? In other words, how do we incorporate A and A0 into this equation?
A minus A naught.
Natural log
What
A.
about the next
Oh
level?
yeah, just
Natural log A.
yeah.
Natural log A.
Sorry.
Okay, so you're saying the natural